Hello, in this lesson let's talk about entropy. So what is entropy and what is its relation to the second law of thermodynamics? Okay, so I think many of you have heard that entropy is a really hard thing to define, right? That we don't know exactly what is entropy, but actually, yes, we know what is entropy, right? We invented this term for a reason. But you can think as entropy as the measure of a system's thermal energy per unit temperature that is unavailable for doing useful work. Okay? So it's that kind of energy that is unavailable. Okay? Cannot use it for produce work. So work is actually obtained for ordered molecular motion. Cannot produce work by disorder, right? And entropy is this measure of the molecular disorder or randomness of a system. Okay? A nice way to visualize this is thinking about a snowflake. So the snowflake is at a very, very low temperature, right? The water is frozen. Everything here looks nice. We have some order. Okay, so the entropy of a snowflake is pretty low. Okay, it's not zero, but it's pretty low, right? As we start to increase the temperature, we start to increase the entropy of the system. So we start increasing it until it boils. And we can see that the motion here, the randomness, the disorder of this molecular motion is very high. So the entropy of the steam, for example, is higher than the entropy of a snowflake. Okay? By this you can visualize what is entropy, what we are talking about. Okay? It's a way to quantify this disorder. Okay, so entropy has a really close relation with the second law of thermodynamics, right? And it's actually like the second law, it's all about entropy. So let me introduce you to the Clausius Inequality. So Clausius Inequality can be expressed using this formula here. And the delta Q here is the heat transfer, okay, at a part of the system boundary during a portion of the cycle. And the letter T here is the absolute temperature at that part of the boundary. This letter B here, just to remind you that all these properties evaluated at the boundary of the system, okay? And this integer, this line integer, indicates that the integral is performed over all parts of the boundary and the entire cycle, okay? And it says that this is always less or equals to 0, okay? Another way that we can express this formula is like this. Okay, so that's another way you can use Clausius inequality. All right, we're just saying that this is equals this another symbol here. So what is this? Well, by this symbol we can define some if the cycle is reversible or irreversible. Okay, if this equation, this left side of the equation is equal to 0, there are no irreversibilities. Okay, if it's greater than 0, well, we have irreversibilities within the system. And if it's less than 0, it's actually impossible. But why, right? This thing here, Q over T, is actually entropy. Is the definition of entropy, okay? And, well, you remember that if the system has no irreversibility, the net amount of entropy is actually 0. But if it has irreversibilities, the net amount of entropy is greater than 0, right? meaning that it's an irreversible process. Well, we cannot have negative entropy, net entropy, right? So if it's less than 0, it's impossible, okay? And that's the thing that when people talk about entropy, they always talk about the universe and that the entropy of the universe is always increasing. But why, right? Why they say this? Well, actually, it's pretty simple to understand. If all the the real processes that happen in the universe are real, they have some irreversibilities present in this system, okay? So everything that happens, all the processes, all the thermodynamic processes that happens in the universe has entropy, produces entropy. So there's no way the universe is not producing entropy, all right? That's why we always say that the entropy of the universe is always increasing, because it's real, it cannot decrease, okay? All right, so another thing we can talk about entropy itself is that the entropy of the system depends on the stage, okay, not the path. So we have state 1 at a certain temperature and pressure, and state 2 at a second temperature, a different temperature and a different pressure. The entropy at state 2 and the entropy at state 1 does not depend on the path. So you can perform a reversible process and go from stage 1 to stage 2, and perform an irreversible process, but also coming from state 1 reaching state 2. It doesn't matter the path here, the process, if it's reversible or irreversible, the net amount of entropy is the same, okay? So how do we calculate this amount of entropy? Well, as I told you, entropy is the amount of heat transferred over the absolute temperature. This for a reversible process, okay? And well, for irreversible process, you can calculate the entropy at this state 2, and the entropy at state 1, and then just do the difference, okay? That's the increase in entropy we have from state 1 to state 2. Alright, so let's practice a little bit. So you have a hot rock that's ejected from a volcano, and it cools down from 1,100 degrees Celsius to 40 degrees Celsius, okay? And we know that the entropy decrease here is 950 joules per Kelvin, okay? So how much heat transfer occurs from the rock? So we can just use the definition here for entropy, okay, the variation in entropy, to find the amount of heat transfer, okay? So we talked about this temperature, the absolute temperature, but what is this temperature here? Well, for each temperature, we actually have a different amount of entropy, right? Here we just have like a mean amount of entropy, right? So we're going to use the mean temperature of these two from like the initial and final stages, okay? For low or small changes in temperature, it's reasonable to do it, okay? In this case here, okay, it's a considerable amount of temperature, right? 40 degrees to 1,100 degrees Celsius. But we already know the mean entropy decrease, all right? So we can just calculate the mean temperature here and add the values. Remember, the entropy here is decreasing, so that's why I have this negative here, okay? And the final heat transfer, okay, the heat transferred that occur from the rock is negative 8 times 10 to the 5th joules. Okay? So it's your turn to think about it now. Explain how the rock's entropy can decrease without violating the second law of thermodynamics. Specifically, explain what happens to the entropy of its surroundings. Okay? So, I don't know if you noticed, but I put a negative sign here. And I just said before that we cannot have negative entropy. Okay, the net amount of entropy is always positive, but I used a negative here. Can you explain why this like decrease in temperature, we have like this decrease in entropy, but how it does not violate the second law? Think about it, and it's not wrong, the calculations, okay? But think about it and write your answers in the comment sections. Thank you.
Physics doesn't have to be hard. Subscribe to our channel and learn with the geeks.